In this warm-up, I emphasize two things. One is the objective of the lesson to be able to find the average rate of change of a function, or when comparing functions between 2 points on that function, whether given a table, an equation, or a graph. And the other one is if the units are given, to emphasize what the units are for the average rate of change. And so I start with number 6, even though it does not provide units in the problem, just to start off with what is a secant line. And I have students look up what a secant line is on their computer, their phone, whatever they have access to at that moment. And so then we look at the difference between those 2 points, the output values over the input values. Just like the slope triangle, we show them, it connects back to the slope formula of a line, and just of the secant line between 2 points on a function that is not linear. And so they use those output values so they can find average rate of change by finding the slope of that line. And so we take the output value of 0.2 minus the output value, or the y value, of 0.1, or a we'll call in this case, and then we subtract the x coordinates, as I'll refer to, b minus a. And so it's just the same as the slope formula. So on number 6, to find that average rate of change of that secant line, you can see that the output values are 5 and 2. And so if we had 5 minus 2 is the output values of 0.2 minus 0.1, and the input values are 1 minus -1, and that's going to be 3 divided by 2, which is an average rate of change of 1.5 across that interval. And we do not have units in this one to refer to, so then we go back to 1 to 5 and we talk about what are the units on 1 to 5. If we find the average rate of change between 2 points on these two functions that represent runner A and runner B, and the units will always be meters per second in this case. You can see on number 1 that the units are going to be, the average rate of change is going to be the same, 120 divided by 9 seconds, because 120 minus 0 is 120 divided by the difference of 9 minus 0. And so those are going to be the same. When you get to number 2, you can actually see that runner B is going to have a higher rate of change from 9 to 20 seconds than runner A, because they are being divided by the same amount of seconds of 11 seconds within that interval, and 213 minus 120 is greater than 168 minus 120. And then you can see that runner A actually catches runner B, and I actually have them calculate this using the same slope formula. And then you're going to have subtracting those output values over the input values. So if they haven't done it at this point, I go ahead and have them try it during the review. And then 287 minus 213, and compared to the runner A, 287 minus 168, over again the same amount of seconds, which was 11 seconds. And you can see that runner A actually catches runner B, and you can see that by the intersection of the graph on those two functions. And then we go to number 9, and we use the same formula again. Also emphasizing if there were units, to do use those, but the units were only represented in the warm-up in 1 through 5, which was meters per second. So number 9 doesn't have units either, but it does give them a function, so they can use the function y equals, or f of x equals x squared. And so then they can substitute in those y values. So the output for, if you substituted in 5 squared would be 25, so that's going to be the output value of the second point. And if I substitute in 0, that's going to be 0 squared, which is 0. And over how many, over what interval, 5 minus 0 would be 5, so it's going to be 25 minus 5, which is an average rate of change of 5. And again, it doesn't give units in this problem, so I just have them state the 5 as a quantity.